Thanks a lot, Carlos, and thanks a lot to Carlos and Ivan for setting up this event, which is really very interesting, exciting. I think it will strongly reinforce my general education in physics, which I think is really the purpose of these kind of events. And today, what I'm going to present you is kind of an overview of using driving and dissipation to stabilize the many body states in a fluid of light. I see in the audience many people who work more or less in the domain and who are certainly much more expert than me on specific points of the talk. So I invite them just to interrupt me and say if I'm wrong, just jump in the discussion. Don't be shy. Since this is a very big field, I will give an overview which is forcedly kind of personal. So my preliminary apologies for if I'm missing some part of the literature. I'll try just to convey some vision of the field, which has been driving me in the last kind of 20 years in investigating this physics. So first thing is to introduce what is a fluid of light. Because normally we are used to speak about many kinds of fluids. It can be neutral, charged, can be atoms, can be electrons, can be helium atoms. But all of them are typically formed by particles which are material particles. Helium atom is an atom. Electron is an electron. So something which is, at least in our perception, is something material. Fluids of light are completely different objects where the basic constituent of the fluid is a photon. So a particle which normally has no mass and normally does not interact with anything. So if you send a couple of laser beams crossing each other in any normal medium, they will basically go through each other as if the other one was not there. And indeed, Maxwell's equations are linear equations. Basically mean one beam, another beam, the superposition of the two beams is again a solution. So normally, at level of Maxwell's equations, no interactions between photons. Again, photons are massless particles in vacuum, so you could think that it's hard to create a fluid of them because, say, they always travel at a speed c with nothing happening of very interesting. The first topic I'm going to cover in this presentation is a platform which is very popular, which has been used in the last kind of 30 years to generate quantum fluids of light where photons acquire a mass and photons display sizable photon-photon interactions. And these are the two basic ingredients for an assembly of particles to develop collective behaviors like a fluid. Like air, this is full of molecules, which are massive objects, which go around our room, collide with each other, so to develop collective behaviors. To obtain these with photons, the first thing is to obtain a mass. In order to get a mass to a photon, the simplest strategy is to take a pair of plane parallel mirrors. In this way, the electromagnetic field has to have nodes on the metallic mirrors. So the wave vector along Z will be quantized in units of pi over the size of the cavity, Lz. So the energy of a photon will be Kx squared plus Ky square. So A photon which lives in this cavity has momentum kx, ky along the plane, has an energy which is the sum of the contribution of the motion along z plus the motion along the plane. If we only consider the motion along the plane, this part plays the role of a mass, like we learn in relativity. Relativity energy is c square p square plus mc square.
Traditionally, you use a left-handed coordinate system or you use a right-handed coordinate system?
Doesn't matter at all here. Okay. So you see that the equation for classical photons in a two-dimensional plane parallel cavity has a dispersion law which is the same as particles in relativity. So the confinement along z is the same as the mass. People often say that the mass of elementary particles comes from confinement of their fields in extra dimensions beyond our four traditional ones. Here, for a small ant working in the planar cavity, the photon field acquires a mass because of the third dimension. Very simple. This is the trick to make photons to have a mass. If we consider the lowest mode, n equal 1, the one without nodes in the vertical direction, k parallel, here frequency, one has the cutoff, and this is the dispersion. So the photon acquires a rest mass and a kinetic mass. So the rest mass is basically the energy of a particle at rest. The kinetic mass is basically the curvature 1 over m is related to the second derivative of the dispersion along k. So getting photons to acquire mass is something which is very easy in experiments. You just buy two pieces of metal, you put them next to each other, the photon between them becomes a massive particle. Okay? So point 1 solved. Photons can have a mass. Point 2, how to make photons interact. First question for all of you. Are you sure that photons do not interact in vacuum? In Maxwell's, of course they do. They don't interact. Maxwell's equations are linear. So you have two solutions, one beam, one beam. The sum of the two beams is again a solution of Maxwell's equations, so no interactions. But what happens at the level of quantum field theory? There are diagrams in QED where photons can interact by exchange of electron-positron pairs. These are Heisenberg-Euler terms, or Heisenberg-Euler-Lagrangian terms. One can estimate what is the cross-section for photon-photon scattering of these is some number that I don't remember, alpha to the fourth, 4 vertices. Compton wavelength square to give the dimension. And the last term is to the 6th. So is the frequency of the photons divided by the rest mass of the intermediate particles that we are creating. Which means that if we work in the visible, where omega is of the order of 1 electron volt, this term is a killer. Is 1 over 10 to the 6th to the 6th. So 10 to the minus 36. Since the prefactors in front are not big, alpha to the 4th quite big, small, Compton wavelength also small, this is basically 0. It's something which is almost impossible to observe. And indeed, the only evidence for this process comes from high-energy experiments at Atlas, built in a very sophisticated way. So I have no time to discuss. It's a Nature Physics paper around 2017, gives some evidence of this photon-photon scattering. But from this form, you should be able to propose me what is the way to gain 36 orders of magnitude. What is the origin of this term? Basically, yes, exactly, the mass of electron, but how does it come into the business? Is the detuning of the intermediate states in perturbation theory. So if instead of working with Feynman diagrams, which are often a kind of black box, we consider perturbation theory as we learn from undergrad quantum mechanics, we can see that the process can be seen in this way. So we have one photon which generates electron-hole pair, another photon hit, then scatters again, and then the two electron and positron recombine. So you see that these are all intermediate states in perturbation theory. Each of them gives the detuning. In the matrix element is the detuning cube. In the scatter cross-section is the square of the matrix element, so it's to the 6th. So what is the way out to reduce this killer factor? Is to allow for intermediate states which are not electron-positron. What is the object which resembles electron-positron in our daily life? Semiconductor material, valence band is full, conduction band is empty. We create a hole by promoting an electron up. This is a sort of positron, this is a sort of electron. Since the gap of a semiconductor can be chosen to be 1 electron volt, more or less, you gain 10 to the 36. Which makes this effect something which can be observed with reasonable lasers. And indeed, all these kind of diagrams are behind the nonlinear optics. So much of what I'm going to say is a reformulation in modern words of something which is known in nonlinear optics. Just that having a different view gives new ideas. So if you have a good statue, it's good to also look from all the sides. You can have surprises. Good. So mass of the photon, interactions between photons. We have everything to build a quantum fluid.
So you just put dielectric in here, nonlinear with some chi3 term.
Exactly. That's the idea. Yeah, no, exactly. That's the idea, Carlos. So I was not precise. That medium can be put inside. You get the mass and interaction between photons. So on paper, one is done. You can do all many-body physics you wish with this system of photons. Of course, there is the interactions, which typically are not that big. So you need to engineer the material in a good way to get into interesting regimes. And you need to do something else that I'm going to say in a second. But concerning the interactions, I've given here a very crude model of photon-photon interactions with this diagram. Of course, life is not this. It's much more refined, much more sophisticated, especially if you want to have a medium with a nonlinearity which is significantly large to be used in experiments. To this purpose, for these quantum fluids of light, one often uses materials with very peculiar properties. One of the most famous has been exciton politons in semiconductor microcavities, which have been the main workhorse for this field in, say, starting from the 90s until quite recently. Now, there are other platforms which are somehow taking over because they provide much larger nonlinearities, which are superconductor devices, so systems where microwave photons are coupled to optical transitions in superconducting materials, in the so-called circuit QED world, or Rydberg polaritons in atomic gases. Basically, atomic gases which are dressed in a way to reach a highly excited Rydberg state. Rydberg states are big, they have huge dipole moments, and they interact with each other a lot. In this way, the interactions between atoms are transferred into interactions between photons. And one can get to regimes which are completely opposite to the one of Maxwell's equations. Basically, photons which are effectively impenetrable objects. So photons become bowling balls, something big and rigid. But we will come to this later on. There is anyway another problem which is often very nasty for this kind of systems. How long does a photon live in a cavity? I don't know if you have ever asked yourself these kind of questions. Typically not much. If you don't make efforts, can be picoseconds, nanoseconds. With very good cavities, you can go up. There exist cavities in milliseconds. But in any case, it's a finite amount of time. So this finite amount of time means that either you are very fast in doing the experiment before photons are lost, which is a strategy. Many groups are using this strategy, especially in the circuit QED world, where the lifetimes can be quite important compared to the other parameters, of course. Or if you are in optical systems with visible light or infrared light, that's typically impossible. There exists no system where the lifetime is long enough to do any interesting physics before losing the photons, except for some specific experiment. So how can you do it? How can you circumvent this difficulty? Cavity. So instead of doing the experiment by loading the cavity and then doing the experiment, as anybody does in cold atoms, what you do, you keep a pump switched on, which continuously replenishes the gas of photons. So photons here are lost at a rate gamma. You put something here, laser beam, of course everything in optics is done with lasers, to replenish the fluid of photons, so to have a state which, in the simplest and typically most interesting configurations, is a driven dissipative steady state. When I say driven dissipative, I mean that the system is being driven by the pump and is dissipative. So the system will have some steady state, which is not a thermal equilibrium, not at all a thermal equilibrium. It's between something which is extremely hot and something which is very cold. Pumping is a sort of infinite temperature. The losses are effectively zero temperature, and the system is in between. So its state will depend on the details of the coupling to the two forces. This, of course, makes all thermodynamics not to be applicable, because the system is not thermodynamic equilibrium. The state of the system has nothing to do with e to the minus beta h. But at the same time, it makes things much more exciting. You can do a lot of things. You can design pumping and losses so that the fluid of photons will be in the state that you wish. You can make the photons do something that particles at equilibrium will never do. And now I'm going to tell you a few examples of things that can be done which are unique of these non-equilibrium systems. Before that, I wish you to point out a couple of important things related to these losses. So the fact that photons continuously escape from the cavity means that you can put a camera and watch them. So you can get information in real time of the evolution of the fluid. If you take an image in a real space, use near field. You take a near field picture of an object, you get information on the real space distribution. If you make a far field image, you get information on the momentum distribution. If you do interference, you can get information on the phase. If you do photocorrelation measurements, you get information on the quantum statistics. So you have access in real time to many more observables that one is used to have in other material systems. Liquid helium, you basically can only watch it, cannot do much more. Electrons, one typically does current measurements or a bit of optics. Cold atoms, there are a lot of things that can be done, but typically are destructive. In most cases are destructive. You have to open the sample and look at it by detecting the atoms. Here, you can let the system run for a full day, and you acquire images continuously. And since the characteristic time scale of these systems is nanoseconds, you understand that you acquire a huge statistics. So you can measure very fine details of the state of the system, because you acquire with a huge statistics on the observables. Of course, the fact of being driven dissipative has another negative phase. One has to remember that whenever you have a loss channel, you have 0 point quantum fluctuations entering the system. Anybody working on squeezing knows very well that coupling to the external world is nasty. Quantum fluctuations of the vacuum enter into the system and dilute your squeezing. And that's something which, of course, exists also here. You have to really deal with that. So, deriving dissipation, you can generate the fluid inside in many different states. Before entering into what can be done in experiments, it's worth writing the mean field theory for this system, which allows to make a comparison to what is the usual know-how for cold atomic gases. Since standard optical systems fall in the category of dilute systems, mean field theory is a good description, as it is typically a good description of bosonic condensates. In the second part of the presentation, I will enter into a regime of strongly interacting, where, of course, the mean field does not hold. So, mean field theory will be a partial differential equation for the electric field in the cavity, where E is an object which depends on the position in the plane and on the time. Along Z, everything is assumed to be frozen in the lowest cavity mode. So, what will be the evolution? We will have the rest mass of the photon. Then a term which describes the quadratic dispersion around the band edge, and doing a sort of Galilean approximation to the relativistic dispersion. This will be note that this H bar is not really a quantum object. Here, mean field theory knows nothing about quantum mechanics. It's just put there for convenience, so to have the usual mass. Here, mean field theory is a classical theory. Then we have some external potential in the plane, which can be generated by deforming the shape of the cavity. For instance, doing a bit of bump in the cavity would be an attractive potential. Then the nonlinearity gives a nonlinear interaction term, which is very similar to the one coming from the interactions between atoms in a condensate. And of course, this will be multiplied by E. So this is nothing else than the standard GPE that we know from cold atoms. Now we need to include something which is for driving and dissipation. But dissipation at the simplest level will be some loss term. Pumping is more sophisticated because it can occur in many different ways. We can have a coherent pumping where the laser field hits the cavity, and this laser field basically transfers its coherence to the photons in the cavity. In other words, this means that this laser beam just goes through this mirror, because this mirror is not fully reflecting, enters a bit in the cavity, and drives the field in the cavity. So this term, which is an external force, which depends on the position and on the time, it's basically proportional to the amplitude of the driving field. This term you can calculate just by doing a Fabry-Perot interferometer. There is nothing more than that. And then, last term, there can be a so-called incoherent pumping term, which is typically modeled in this way, like a saturable gain term. And this describes light amplification when something is put in the cavity medium, when some gain is present in the cavity medium. In the first generation of polariton condensate experiments, this was obtained by injecting from the exterior some electron-hole pairs in this material, which give population inversion for the electron and holes, and then give gain. So what I'm presenting here is this mean field theory. It's something which was well known in nonlinear optics, in laser theory, since several decades. You can find it called the Lujato-Lefebvre equation, Lam's semiclassical theory of the laser, complex Ginzburg-Landau equation. It goes under very, very different names. And typically, each community has looked at it from a different perspective. And none of them has used the language of of many-body physics. So typically, people in optics don't use the language of many-body physics. At the level of optics, when it's mean field theory, is not a problem. Everything can be extracted in whatever language. The problem is that using a language which is closer to many-body theory is useful then to move on in the world of strongly interacting photons. When nonlinearities are strong, mean field theory becomes shaky, and you need to take into account all the many-body coherences. For that, having a language which is a many-body physics one is extremely advantageous. Before entering into that, it's interesting to give some ideas of what can be studied at the level of mean field theory. What are the surprising phenomena that one can obtain in this context? So, historically, the first generation of experiments with fluids of light was done with this kind of pump. And were done at LKB in Jussieu, a group of Alberto Bramati and Elisabeth Giacobino, where they investigated how these fluids of light can display superfluidity properties. We know superfluidity is a very general phenomenon. It has different aspects. The one that they investigated was the fact that a fluid can move along the plane with some speed, hit some defect. The defect is an external potential in the cavity. In their case, it was an unintentional defect. It was just a scratch in the cavity, a fabrication imperfection. And if the fluid is superfluid, there will be no friction given by the defect on the fluid, so no friction force felt by the fluid, and at the same time, there will be no disturbance generated by the defect in the fluid, except for something very localized around it, if it's superfluid. If it's not superfluid, this defect behaves like a stone which moves in a classical fluid, or a plane through air, which means that it will create a wake around it, and in front there will be some other wavy lines. And the fact that this modulation appears in the fluid is a signature of the fact that the defect excites the fluid. So kinetic energy of the fluid will be transferred into collective excitations of the fluid, inducing some friction on this defect. So these two regimes, in this formalism with an external force, can be induced just by tailoring the external force as some single frequency component, monochromatic light, to generate the fluid at the correct frequency close to the good resonance position, and some in-plane wave vector. Putting a force with some in-plane wave vector, you see from the form of the equation, the plane wave here will transfer to the plane wave in the electric field. So the fluid will start moving at a speed v, which will be h bar k over m. From the general theory of superfluidity, if v is larger than the speed of sound, one breaks superfluidity. If the speed is smaller than the speed of sound, superfluidity can survive. Superfluidity can survive, there is no friction, nothing is generated in the fluid. Here is the opposite. Speed is too large, there will be a wake behind the defect. Yes?
Your argument that in the superfluid there is no wake.
You see here why there is no wake. This, you can see it really in this way. If you take the Bogoliubov dispersion in the fluid, this would be the dispersion normally. Since the fluid is moving, one has to Doppler shift it. This will be high speed. Lower speed, the dispersion will be like this. So you see that if the speed is too small, a defect which is at rest, which can only excite modes which are at zero frequency.
That's true. That's sort of just the argument in a way. No. But I mean, actually, honestly, I've done a calculation a long time ago. There is a bipolar backflow in the superfluid, which goes out long, but it doesn't produce any friction.
Wait, you say backflow here. This is a perturbative calculation. It's for weak defects.
Okay, we can discuss it later.
Yeah.
I think so. I don't agree with this simple story.
Okay. This basically what we did was just a linearized GP. We take the GP, we linearize with respect to a weak potential. So if the potential is weak, can only excite modes at its frequency. So the only here, if the flow is too weak, there is no mode at zero frequency, so nothing can be excited.
See, you're calculating the state sort of in the absence of security.
Of course, it's perturbative.
That's not allowed if you want to treat this problem.
Okay, yeah. Because you have to, you see what you're saying really is that you have to go to the all orders in perturbation theory.
Yes.
Even if the defect is large, spatially large. So you say perturbation series does not converge.
Yeah, I mean, this backflow problem is an old story. I mean, you look in Mosier Pines, they tell you about this backflow. Actually, also they miss something.
Okay, so anyway, say the experiment was done, and the experiment saw that when the speed is small, the amount of all these perturbations is basically negligible. When the speed is large, this perturbation shoots up with a clear threshold at the speed of sound. Of course, the system is dissipative. So I've put a bit under the carpet the fact that a resonance condition is not exact in a dissipative system. So everything is a bit smeared out. So instead of having exactly 0 and then going up, one gets something which is a bit rounded, but with a clear threshold for low enough dissipation. The first measurement here in Paris was done looking at the density distribution in the fluid of light. Afterwards, an experiment in Nice was done on a different platform of fluid of light, where they were able to measure, with an extremely smart idea, to measure the friction force that this defect feels. And what they saw is that for low speed, basically there is no friction felt by the defect. For high speed, the defect is pushed. So if you put a stone in a superfluid, and the superfluid flows slowly, basically the stone does not feel any pressure from the fluid which goes around it. If the fluid is too fast, then superfluidity is broken and the stone feels some pressure. And this was measured in a very smart, all-optical way in the group in Nice. Yes, sir. It's an all-optical stone. No, the all-optical. They used, Matthias, perhaps you can say something more. It's another laser beam. It's an optical stone. It's another laser beam.
But then if it's an optical stone, then it becomes even more complicated than what Julian was saying, because then the fluid of light presumably would also interact with that. Not as an impurity, but
it interacts via such a potential.
Okay, and you say it doesn't matter. There's the issues of backflow also from photons from
the two cannot exchange photons. They have different color. One is red, one is green. Photons cannot be exchanged. The only interaction is some potential term after cooking up everything. And they saw that putting this laser beam to create a defect, if the flow is low, this keeps going straight. If the flow is too fast, this beam starts being bent. So it's a measurement of the friction force done by superfluid onto system or not. Good. So these were the first generation of experiments, which seem very similar to what one has in standard gases, but there is a technical point which has not to be forgotten, which is that here the oscillation frequency of the field is set by the frequency of the laser field that I'm using to drive the microcavity. So there is no this relation that typically one has at the mean field level in a condensate, where the chemical potential sets the oscillation frequency of the matter field. Here, the frequency at which I'm driving the system is not equal to the density in the gas. So one has one more degree of freedom, and that's typical of non-equilibrium. the two quantities are somehow disjoint, and this gives more freedom in the dispersion of Bogoliubov modes. Normally, in equilibrium condensate, Bogoliubov mode will be this, with the, say, the Gauss branch below. Here, with different choices of omega, one can get Bogoliubov dispersion, which is gapped, Bogoliubov dispersion, which has two regions which are close to becoming unstable, and many other in much higher variety of zoological configurations. So non-equilibrium makes many more things possible. So this is for coherent pumping. Another generation of experiments which were milestones in this adventure were based on using this kind of pump. And you note that the symmetry is very different. Here, the phase symmetry of the field is broken, because this field sets a preferential phase for the field E. Here, with this kind of pumping, the phase symmetry is preserved. So one has a spontaneous symmetry breaking mechanism. This spontaneous symmetry breaking mechanism is very similar, or perhaps identical, to the one that one has in lasers. Actually, this equation is the Lamb's semi-classical laser theory. So the physics must be the same. So from this language, one may say that some standard condensation should be obtained. But also in this case, there are some interesting subtleties coming from the fact that one is non-equilibrium. In particular, solving this equation without this term and breaking the equation in the real and imaginary part and performing a sort of LDA equation, one gets that the local density will be something with a threshold, so it will be 0 below threshold and this other formula above threshold, where only the modulus of E square is determined. The phase basically remains free, spontaneous symmetry breaking. And the oscillation frequency omega is chosen by the system itself according to its own will, basically solving this equation, and has this property that within a local density picture, it be set by this equation, which tells you that if the system condenses in a state with a given frequency, with a single frequency omega, this equation must be satisfied at all positions, which means that if the density profile of the condensate is not uniform, this change in energy must be compensated by something else, which typically is the speed. In practice, this looks a bit abstract, but in practice, if you have a cavity, your planar object, you drive it with a pump spot which is quite small, you obtain a condensate which will be very localized in space. So here, the interaction energy will be much higher than outside. So this extra interaction energy must be compensated by a kinetic energy. So the solution to this equation that you obtain by means of any numerical solution of the differential equation will be that the condensate will flow out. So the distribution of speed will be very non-trivial. In the center, particles will be at rest, and then they will acquire kinetic energy when sliding down the edges of this mountain. Since the condensation process occurs where the density is already present, because it's due to stimulated emission, condensation will occur mostly at the center, and then particles, or photons, will slide down the sides of this mountain. It's like a volcano effect. Lava is generated at the top and then slides down the edges of the mountain. So if you take the momentum distribution for this condensate, it's not the usual condensate at k equals 0, which would be at equilibrium, but has a momentum distribution which has a shape which is centered in a ring in the plane kx, ky. And this was experimentally observed in one of the pioneering experiments in condensation by Max Richard. He was a PhD student in Grenoble at the time. He observed this very strange momentum distribution with a ring shape. And it took a bit of time to convince ourselves what was the origin of this effect. Then there were later experiments done in the group of Jacqueline Bloch, then it was LPN, where they measured the momentum distribution spatially resolved, and they found that here the momentum distribution is peaked at a positive k, and here instead the distribution is peaked at a negative k, confirming the theoretical model. So this is an example of how non-equilibrium completely changes the properties of a phenomenon as simple as condensation. Since there are spontaneous symmetry breaking features, you can expect to have, via the Goldstone theorem, a Goldstone mode which is soft in the limit of k tending to 0. So the global rotation of the order parameter will be a soft mode. So theoretical calculations were done by Michiel Wouters, and he found that the Bogoliubov dispersion for this incoherently pumped condensate has a dispersion whose real part is flat up to some point, then goes up, the same side, of course. And the imaginary part is 0 at 0, and then has these points correspond to this point. So at low momenta, so long wavelength excitations in this system will be diffusive. 0 real part, parabolic imaginary part. Of course, Goldstone theorem is satisfied at 0 is at 0. So Goldstone exists. So omega k tending to 0 is 0. But it does not go to 0 as it happens, for instance, in an atomic condensate, which has this form. This would be sound wave. It goes as minus I alpha k square, which is the Fourier expression for a heat equation. Plus for the heat equation. So the density perturbation in a non-equilibrium condensate do not propagate like sound, but they diffuse like heat in a medium. That's a very strong difference in the two systems, which was experimentally observed kind of 1 year ago in the group of, again, of Alberto Bramati in Jussieu. He saw a bit more sophisticated version of spontaneous symmetry breaking. I have no time to explain the details, but the idea is to measure imaginary real part. Please, Carlos.
That's a very naive question, maybe even stupid, so I can complete my education here. When I think about Goldstone modes emerging from spontaneously broken symmetry, let's say, of any type you choose, in this case, something like U1. Now you have a non-equilibrium system that comes in. So I always derive those things, you write down a Lagrangian and so on, and everything is conserved, everything is nice. So how does the Goldstone mode emerges in this case?
You see here from this equation, if you have a solution E, if you take another solution which has this form, it's still a solution.
Honestly, I think it's a misuse of the name of Goldstone.
Yeah.
Sorry.
That's what I was trying to get.
Goldstone tells you that sort of in a system, there's an exact eigenstate that sort of, approaches zero. This is not a system which has an eigenstate. So you can use the name, but I think it's sort of a completely different story.
It's, you have a mode which is soft.
Yes, it's a diffusive mode.
It's a diffusive mode.
It's not a Goldstone mode.
No, but you have a mode which is soft as k tends to 0.
It's a free country. You can call everything. I think it's sometimes creates confusion.
You have a symmetry, you have a soft mode which appears, which tends to 0 as k tends to 0.
Goldstone theorem, right? There are some hypotheses. So what are those hypotheses?
Basically, here I have a symmetry which is spontaneously broken, and I have nothing special happening at small k. So basically, I have no long-range interactions. The question is completely local.
So the point raised by my colleague that in the Goldstone theorem, do you assume that there is a conservative system with the Lagrangian, for example? Or?
Typical derivation do so.
Yeah, he doesn't have a Lagrangian.
No, here, Jose, you could write, I think, some Lagrangian, but I think it's not really the simplest way to see the system.
Anyway, one has to look at the hypothesis
Yeah.
of the theorem.
No, the theorem, hypothesis of the theorem are not satisfied. But still there is a mode which is soft.
Let me put it this way. You being very kind to Goldstone. I'm sure he's happy on his grade, but I would not call that a Goldstone mode either. Anyways, that's cool.
Okay, good. So anyway, what experimentalists have seen is that there is dispersion has a flat region and a line width which gets very narrow when tending to k equal to 0. So it's a narrowing of the dispersion much lower than the value asymptotic at larger k's. To see that this effect is really connected to a spontaneous symmetry breaking phenomenon, the trick is to explicitly break the symmetry. To explicitly break the symmetry, you go back, you introduce again this term, which is a term which is not invariant under this transformation. So it chooses a specific phase for the system. So the condensation will occur with a special phase. repeated experimental measurement of the dispersion, and they found that this imaginary part stops tending to 0. It gets gapped. And the amount of this gap depends on the strength of this pumping strength. This shows that removing the symmetry which was underlying the softness of this mode, one makes the mode to be gapped. This shows that the symmetry is behind this light narrowing phenomenon. Good. Okay? So far I try to give you an idea of what can be done at mean field level. Now let's move to the regime of strongly interacting photons. To this purpose, doesn't matter. Okay. So now to get photons strongly interacting. So the simplest thing is to take a cavity. Let me draw it in the simple way. Fill it with a nonlinear medium, which is so nonlinear that the state with 2 photons in the cavity is shifted from twice the energy of the single photon state by an amount U, which is much larger than the cavity line width. So interactions between photons are so large that they shift the state with 2 photons by an amount large compared to the losses. So if I put a laser which goes from 0 to 1, this injects 1 photon, but is not able to inject a second photon in the cavity, because the energy would have to be different. So as a result, the cavity behaves like a 2-level system. Photons are effectively impenetrable particles. This is typically called photon blockade. Photon blockade effect, where the presence of a photon blocks the entrance of a second photon in the cavity. So in single-mode cavities, this has been studied in many different platforms, in many different ways. It's a typical building block of quantum optical devices. What is interesting for the point of view of many-body physics is to combine several such elements together. So the simplest thing to do is to build a necklace of these objects. Let me take, for instance, a pentagon. I'm putting 5 of such cavities. 5 just because I like pentagons. So what happens if you do spectroscopy on this system of 5 sites? If your laser field is very weak, it will basically only drive transitions to single photon states. So from your ground, which is vacuum, you will drive the system to states with 1 photon. You will have a few states. Basically, you will have 5 eigenstates with a single photon. These are states with n equal 1. This is vacuum n equals 0. So, making just a spectroscopical experiment, looking at the amount of photons which are in the system are then transmitted on the other side, one will see a few peaks at the frequencies of these from the vacuum to these states. We draw them. 5 peaks in the generic case. What happens then if you drive the system harder? You will start injecting more photons in the system. So you will be able to start feeling what happens in the manifold with 2 particles. So how will this state appear in the spectrum? Basically, you will have some peaks whenever a 2-photon transition hits exactly an n equal 2 state. And this will put in our spectrum, let me build it, draw it a bit larger. These are the 1 particle peaks. There will be additional peaks corresponding to n equal 2 states. What are the frequencies of these peaks n equal 1? They will be basically at the difference of an eigenstate of n equal 1 minus the ground state. The peaks at 2 particles will be instead at omega n equal 2 minus omega naught over n equal 2. Because you have to go via a 2-photon process. Then you have the n equal 3 up to n equal 5. Impenetrable photons, we can at most accommodate 5 particles.
So the single lines are transitions between n equals to 1 and n equals to 0 manifold?
The straight ones are from 0 to 1. And these are the ones which are visible at very low power. When you start ramping up power, you have other lines whose intensity grows as I square, which are 2-photon resonance. Omega n equal 2 minus 0 over 2.
Okay, so that's a transition per photon, right? So that's the
Exactly, it's the frequency of your laser. This is, say, omega laser. Let's write it like this. It's omega laser. Then, if you drive harder and harder, you can excite 3-photon, 4-photon, 5-photon transitions. And every peak will be at omega n minus omega 0 divided by n. And this is a way you want to study this state. You put a laser which is exactly at 1/3 of its frequency. So in this way, you drive that system. You can measure the correlation functions of the light in the pentagon. And these correlation functions will be the same as the ones of the many-body state that you are exciting here. These are eigenstates of the many-body system. I'm putting under the carpet a weak loss condition. So basically doing the standard theory for lossy systems, Born-Markov. So, but anyway, I'm able to address specific states, the specific many-body states. And here, what are these many-body states? Will be complicated states if the fluid is composed of impenetrable photons. Particularly, it will be a discrete version of Tonks-Girardot gas of impenetrable photons. Basically, it's a system whose eigenstates I can calculate analytically by means of fermionization techniques. This was very convenient because I was able to really look at the peaks in the numerical spectrum and attribute every peak to something that I knew from analytical calculation. So all these positions were exactly known. Good. So this was the first calculation was with this a bit silly pentagon of cavities, which is of moderate interest, except for analytics. But what happens if instead of this configuration, I have a lattice of cavities, say, let me put it like this, a checkerboard of 16 cavities where each plaquette is pierced by a magnetic flux. Of course, it's a synthetic magnetic flux, so it's a synthetic field acting on photons. This has been engineered in topological photonics. I have no time to discuss it, but there are a lot of research developing magnetic fields for photons. Sounds very weird, but basically it means configurations where a photon does not go straight, but does cyclotron orbits. So, what do you expect to see if you did a similar experiment in this case? Photons are impenetrable and subject to a strong synthetic magnetic field. What will be the eigenstates? If you don't know it, it means you were sleeping this morning. The Laughlin levels without interactions, Laughlin levels with interactions. So you can discrete, because this configuration is discrete, but there are states that you can calculate almost analytically. Those are the Laughlin states, the discrete version of Laughlin states, with peculiar phase properties and all that we know. So if you want to generate a Laughlin state of a few photons, you only have to build an array of cavities, photons impenetrable, synthetic magnetic field, and then you do this kind of spectroscopy experiment. You say, I want this Laughlin state here. This is the Laughlin state I like. I tune the laser to be 1/3 of this frequency. My many-body state will contain a high percentage, high population of this state. I take the light coming out of the system. I measure the correlation functions. These have the very complicated structure of a Laughlin state. This was experimentally done. Not exactly in this way, but in a much more clever way, as experimentalists always know how to do. Theoretical proposal was absolutely cumbersome compared to what John Simon invented, which is basically to use a cavity, an optical cavity, which is non-planar. So a ring cavity, standard ring cavity, where the ring is tilted out of plane, like a boat. The effect of having a tilt via the periscope effect makes the photon to feel a synthetic magnetic field for their motion along the plane of the cavity. It's very well discussed in the original papers by John, but so believe me, if you want, we can discuss it a bit later. But it was a kind of uovo di Colombo, we would say it in Italian, to generate a synthetic magnetic field of light just by creating a cavity which is not flat. Then John put some Rydberg EIT medium at some point in the cavity to obtain strong nonlinearities. In this way, had strong interactions, synthetic magnetic field. So the eigenstates should be Laughlin states. He did exactly this spectroscopy trick. Vacuum, one photon manifold, Landau levels are basically flat, two photon manifold, there is a Laughlin state plus some interacting states. Laughlin state is the one where the wave function is 0 at the contact point. So putting a laser which is exactly on these two photon resonance, he and his collaborators were able to create a Laughlin state of photons. This Laughlin state has the usual form times the Gaussian, which has peculiar properties, both in real space, which basically means that two photons cannot be at the same point. They have a relative angular momentum. And this also has very peculiar properties in angular momentum space. It's enough to rewrite this polynomial in this way, which means that either I have one particle in the state L equal 2 and one particle in L equal 0, or I have two particles in L equal 1. So making the correlations of the light which exits the system, I can characterize tomographically that what has been generated is indeed a Laughlin state of photons, which is extremely cute, but has the problem that two particles are not really the thermodynamic limit. And there are not even three. So it's a kind of a bit limiting simple case. The idea anyway on paper works up to higher numbers, and I think that at some point John will try to do the experiment, yes. He moved to Stanford in the meanwhile, so perhaps he had other things to do. But conceptually, anyway, there are some limitations. I cannot use this technique to go to the 10 to the 23 photons. Basically, there are two nasty things which make this protocol not really effective. One is that you are injecting photons all from the same source. And this source has a very precise phase shape. And the overlap with the state, which is a Laughlin, gets basically to 0 very fast with the number of particles. Second problem is that this denominator, n, means that if this object is the many-body gap, my shift in frequency between the state and the state above my many-body gap will be divided by capital N, which becomes very small when you go to high ends. So there are two reasons for this method to work only up to mesoscopic numbers. But already seeing it at play for 3 particles, it would be a wonderful achievement. Coming to the title of the presentation is what can be done to stabilize states which are large and strongly correlated. So the idea that is one of the most popular at the moment is to use an incoherent pumping. Basically, the reason why to choose this is quite simple. You have a two-level system. If you drive the system coherently, as we did here, the best you can do is to have half a population up, half a population down. That's standard quantum optics. If instead you put an incoherent pump up, as soon as the incoherent pump is larger than the losses, population will go to the upper state. That's basically how people do population inversion in lasers. The problem that in our case, we want something slightly more sophisticated. Let's consider generic state which is protected by a many-body gap, fractional quantum Hall or Mott insulator. So the idea you have something on the lowest states, then you have the state that you want to target, which is separated by a many-body gap from something else. Particularly in FQH, you have that all these states are non-interacting, so zero energy, except then up to here, this is separated by a many-body gap from the next one. Sorry, let me do a drawing a bit better. So this is the state we want to target, which is separated by a many-body gap. Then the state with one more particle, since the size of the system can be tuned to be finite and well-defined, you have that the next state will be up by some many-body gap. You get to your target Laughlin state. If you want to put one extra particle on top of it, you have to pay the many-body gap, because you have no space to expand your system. So if you use this standard incoherent pumping is Markovian. It does not fill the energies. So basically, you do this trick, P larger than gamma, you will shoot all the population very high. You will not fill this many-body gap. If you use instead a non-Markovian incoherent pump, you still have some energy selectivity. The importance is to have a level of non-Markovianity which is enough to go up to here, but not being able to cross this many-body gap. So your irreversible dynamics will concentrate all the population in this final target state. You see, because any time by losses you go down, you lose a particle, then your repumping is extremely efficient in bringing you back. But it will not bring you in the states that you don't want, because these are blocked by the non-Markovianity of this phenomenon. So this is a pump which is not fully Markovian, but not fully coherent either. So one has to choose the level of coherence in between the two limits to exactly obtain what one desires. And you see that the level of Markovianity, say the characteristic frequency of the non-Markovianity, has to be smaller than the many-body gap. And there is no division by capital N. The important point is not to go to this state outside and not to go to these excited states. Then once this is established, one is happy. So the condition is much softer. And the result will be that most of the population will be in the desired state, which is much better than having a coherent pump, which in the best case has a half-half. So experimentally, this idea was in the wake of a series of theoretical proposals trying to implement it in different ways, a few variants, a few flavors of this idea on the market. But what was realized by, again, Jonathan Simon was he built a chain of lattice sites. On each of them, interactions between photons were extremely strong. He put a pumping mechanism, which for technical reasons was only on the last site. And the result was that at the steady state, he had a chain, I think were around 8 sites, and each site contained 1 photon. So he went to the steady state, made tomography of the quantum state he has in the system, and he found that the accuracy at which he had reproduced the state with a single photon per site was very high. And this system is a sort of Mott insulator of photons. So it's a state where each site contains 1 and only 1 photon. And is an example of many body state involving many particles, many strongly interacting particles. So this is a very pioneering experiment which calls for a lot of new steps to be done, both from the experimental side, but also from the theoretical one. So the main piece which is not fully understood and not fully developed in the theory is the description of the non-Markovian pumping. For this, there are, at least so far, used 2 main strategies. One is to try to use some Born approximation, where assuming the coupling between the system to the pumping and loss bath to be weak, and work in that limit using the typical techniques of driven dissipative systems, allowing for the non-Markovianity, which basically amounts of setting the renormalizing the jump operators by the non-Markovian spectral distribution. Or another trick, slightly more sophisticated, which was developed by a few young people in the last few years, José Lebreuil, Alberto Biella, and Fabio Caleffi, was to include in every site a 2-level system and obtain this pumping emission by means of emission from a 2-level atom. A 2-level atom can only emit light next to its own resonance. So this will pump the effective density of these cavities only when the two are approximately on resonance. And this somehow builds a non-Markovianity of the emission process. So if this emission process is tuned to get to here and not to the other state, this in principle should work. These ideas have been validated on the numerics up to small values, because it becomes computationally very difficult. So up to, say, a few sites, 5 sites, 10 sites in some cases. So before going to macroscopic systems, one has to really do some theoretical work to assess that there are no loopholes on the way. At the same time, there are very interesting questions in what are the collective excitation modes of these strongly interacting many-body states which are driven dissipative. So what Fabio Caleffi started to do a few years ago was to use a Gutzwiller approximation, factorizing the different states, linearizing around a driven dissipative steady state, looking for the eigenmodes of this Gutzwiller equation. And he found some interesting dispersion of modes you can find in some recent papers. But things have been predicted in some, to be even more interesting in the case of fractional quantum Hall state, where the driving and dissipation has been predicted again by José Lebreuil together with Steve Girvin and other people, to be responsible for a diffusive motion of quasi-holes in a fractional quantum Hall fluid of light. Basically, the mechanism is that if you have a quasi-Hall, you can lose another particle next door. Let's say if we have a fractional quantum Hall with Q equal 2, this contains effectively losing a photon means creating 2 additional quasi-holes. Then one refills this big object in this way, putting the extra photon here. So one is left with a quasi-Hall which gets shifted in space. So this includes a diffusive motion of the quasi-holes. You may say, who cares about this? No, this can be very dangerous. Can be dangerous if one wants to use these fractional quantum Hall fluids of light as a platform for topological quantum information. In topological quantum information, normally the most dangerous process is when you exchange 2 quasi-holes, when you braid things around. If the quasi-holes are almost at rest, this process hardly happens. So you can think, at least you can conjecture, that the fractional quantum Hall fluid of light could be a good platform for topological quantum computing. If you make these quasi-holes to wander in space, the probability of having these braiding processes could be much larger, destroying the robustness of the topological protection and making the system completely useless for applications. Of course, it remains very interesting from the theoretical point of view, but it becomes useless for applications. So understanding the details of how the driving and dissipation modifies the many-body physics of these systems can be extremely interesting, even for their use as different objects for technology. I think it's time for me to stop. So thank you for your attention.